There is a difference between the ground moving and the ground changing. Movement is what we measure with seismometers. It is the sudden release of accumulated elastic strain. It is an earthquake. It has a magnitude, a depth, a mechanism. It arrives in seconds and ends in minutes. Jolt is what we measure with GPS networks and satellite gravimetry. It is the slow redistribution of mass across the surface of the planet. It operates over decades and centuries. It does not shake. It shifts. For most of the history of seismology, these two domains were treated as separate. The movement was the signal. The change was the baseline. The baseline was assumed to be stable. That assumption is no longer defensible. The planet is undergoing a sustained anthropogenic rearrangement of its surface mass. Ice sheets are losing volume. Ocean basins are gaining water. Continental aquifers are being drained. The cryosphere is retreating. The hydrosphere is rising. The lithosphere is responding. Not quickly, not dramatically in any single year, but measurably, persistently, and in ways that are beginning to register in the fault systems that produce the largest earthquakes on Earth. This documentary is not about a single event. It is not about the 1997 El Niño, although that event will appear in these frames. It is not about a viral chart circulating online, although that chart will be examined. This documentary is about the physical connection between climate-driven mass redistribution and the timing of great earthquakes. It is about what we have measured, what we are still debating, and what the next several decades are likely to bring. The connection exists. The peer-reviewed literature has documented it in multiple regions. The amplitudes are small per year, but the signal is cumulative, and the cumulative signal is accelerating. What follows is a systematic walk through the evidence, the instrumentation, the mechanisms, the scientific disagreements, the human exposure, the cascading consequences, and the long-term projections that emerge when you take the data seriously without sensationalizing it. Begin with the instrumentation. The modern ability to measure mass redistribution from space began with the GRACE mission, Gravity Recovery and Climate Experiment. 2 satellites flying in formation, measuring the distance between them to within fractions of the width of a human hair. As they passed over regions of higher or lower gravity, the distance changed. Those changes mapped the movement of water, ice, and rock beneath them. GRACE launched in 2002. It operated for 15 years. Its successor, GRACE Follow On, launched in 2018 and continues to collect data. The signal from GRACE was unambiguous. Greenland was losing mass. Antarctica was losing mass. Mountain glaciers were losing mass. Continental aquifers were being depleted. The global ocean was gaining mass at a rate inconsistent with the sum of the cryospheric losses plus thermal expansion. These were not models. These were measurements. At the same time, GPS networks were being densified across the planet. The Plate Boundary Observatory in the western United States, the GeoNet network in Japan, the EUREF network in Europe, the continuously operating reference stations in Australia, New Zealand, Chile, and dozens of other countries. These networks measure vertical and horizontal motion of the crust to within a few millimeters per year. They were designed primarily to measure tectonic deformation, but they also capture the elastic response of the crust to changes in surface load. When the Sierra Nevada rises a few millimeters each year, because the Central Valley Aquifer is being drained, the GPS networks detect it. When the coastal margins of southeast Alaska rise at rates exceeding 2 centimeters per year because the Yakutat ice cap is melting, the GPS networks detect it. When the monsoon loads the Ganges Plain with enough water to depress the crust by several millimeters, the GPS networks detect it. The combination of satellite gravimetry and ground-based geodesy has produced a detailed picture of how mass is moving across the planet. The picture shows a world in which hundreds of gigatons of water are being transferred from the cryosphere and the continents into the ocean every year. That transfer has mechanical consequences. The crust is not rigid, it is elastic. When you add mass to a region, the crust bends downward. When you remove mass, it rebounds upward. This is not speculation. This is elastic plate theory. Confirmed by decades of geodetic measurement, the stress changes associated with loading and unloading are small. A typical seasonal loading signal from monsoon rainfall or snow accumulation produces stress changes on the order of 1 to 10 kilopascals. A kilopascal is the pressure exerted by a stack of 10 $100 bills. The tectonic stress that builds up on a locked subduction zone fault over centuries is on the order of several megapascals. A megapascal is 1,000 kilopascals. The climate-driven stress signal is therefore 3 orders of magnitude smaller than the tectonic stress that ultimately drives fault failure. That gap is important. It tells you that climate cannot cause an earthquake that was not already going to happen. The energy is not there. The stress is not there. The mechanism does not exist. But the gap does not mean the climate signal is irrelevant. It means the climate signal modulates timing. It pushes faults that are already near their failure threshold slightly earlier or slightly later. It clusters events in time. It changes the spacing between great earthquakes. And over decades and centuries, a persistent one-directional loading signal can accumulate. The Greenland ice sheet does not just melt and refreeze each year. It melts more than it refreezes. The net loss is cumulative. The crust beneath Greenland is rebounding, not just seasonally, but persistently. The stress change from that persistent rebound is small each year, but it adds up. After 50 years of accelerating ice loss, the cumulative stress change in the crust beneath and around Greenland reaches tens of kilopascals, still an order of magnitude below the tectonic stress needed to trigger a great earthquake, but not zero, and not negligible when considered alongside other modulating factors. The scientific question is not whether climate-driven mass redistribution affects the crust. It does. The question is how large that effect is relative to the natural variability of earthquake occurrence, and whether the effect is large enough to be detected in the seismic catalogue. That question has been answered in the affirmative for small to moderate earthquakes. The Himalayan monsoon modulates the rate of small earthquakes by approximately 20%. The Japanese snowpack modulates seismicity by several percent. The California groundwater cycle modulates seismicity in the eastern shear zone. The Mississippi Basin loading modulates seismicity in the New Madrid zone. These effects are real. They are documented. They are published in leading peer-reviewed journals. They are not suppressed. They are not hidden. They are simply not widely known outside the specialist literature. For great earthquakes, magnitude 8 and above, the statistical signal is more difficult to extract. Great earthquakes are rare. The global catalogue contains only about 100 such events since the advent of modern instrumentation in the early 20th century. Rare events produce noisy statistics. Noise can look like signal. Signal can be mistaken for noise. The viral chart that circulated online claimed that the rate of magnitude 8 earthquakes increased by 93% after 1997, and that the 1997 El Niño was the cause. The first half of that claim is statistically defensible depending on how you define the windows and how you handle boundary cases. The second half is not. What follows is a methodical examination of the data, the catalogue, the cluster, the debate within the seismological community, and the real climate signal that actually matters for the planet's seismic future. To understand what changed, you have to look at the catalogue. The United States Geological Survey maintains a comprehensive earthquake catalogue called COMCAT. It aggregates data from seismic networks around the world. It is publicly accessible. Anyone with an internet connection can query it. Run a query for magnitude 8 or larger earthquakes between January 1st, 1970 and December 31st, 1996. 27 years. The catalogue returns between 15 and 17 events, depending on how you handle reprocessed magnitudes. Run the same query for the period between January 1st, 1997 and the present. 29 years and counting. The catalogue returns between 27 and 30 events. The raw count has approximately doubled. The annual average rate has risen from roughly 0.56 events per year to roughly 1 event per year. The viral chart reported these numbers as 15 versus 29. That is within the defensible range of catalogue interpretations. The underlying observation is real. There have been more magnitude 8 earthquakes since 1997 than in the 27 years before it. But the viral chart stopped there. It did not ask where the increase came from. It did not ask whether the increase was evenly distributed across the post-1997 window. It did not ask whether the increase was statistically significant given the natural variability of rare event occurrence. It simply asserted a cause. The 1997 El Niño changed things. That assertion is where the science and the chart diverge. Plot the post-1997 events year by year. The increase is not gradual. It is not spread evenly across 29 years. It is concentrated in a specific window that opened in late 2004 and closed around 2018, the first 7 years of the post-1997 window. From January 1997 through December 2003 contain no unusual concentration of magnitude 8 earthquakes. The rate in those years is roughly consistent with the long-term average. Some years have 1 event. Most have none. There is no signal. Then comes December 26, 2004. Off the western coast of northern Sumatra, a 1,300-kilometre length of the Sunda megathrust ruptures in a single event. The moment magnitude is between 9.1 and 9.3. It is the third largest earthquake ever instrumentally recorded. It displaces enough seafloor to generate a tsunami that kills more than 230,000 people across 14 countries. 3 months later, March 28, 2005, a magnitude 8.6 event strikes the southern margin of the same rupture zone. It is a direct aftershock of the December main shock, releasing strain on a segment that did not fully rupture in the initial event. Then the cluster accelerates August 2007, an 8.0 off the coast of Peru. September 2007, an 8.4 off the southern coast of Sumatra. September 2009, an 8.1 in the Samoa region. February 2010, an 8.8 off the coast of central Chile, the 6th largest earthquake instrumentally recorded. March 11th, 2011, off the northeastern coast of Honshu, Japan, the Tohoku earthquake, magnitude 9.1, the 4th largest earthquake instrumentally recorded. The tsunami kills nearly 20,000 people. The Fukushima Daiichi nuclear plant suffers 3 meltdowns. The economic damage reaches approximately $250 billion. April 2014, an 8.2 off the coast of northern Chile. September 2015, an 8.3 off central Chile. September 2017, an 8.2 in the Gulf of Tehuantepec off the coast of Chiapas, Mexico. Count them. December 2004 through September 2017, just under 13 years. 9 unambiguous magnitude 8 events. If you include several borderline cases, the count reaches 11 or 12 in 14 years. The long-term global rate of magnitude 8 or larger earthquakes is approximately 1 per year. Over 14 years, the long-term expectation is 14 events. The observed cluster is therefore not statistically extreme. What makes it unusual is not the total count. It is the sequence, the temporal concentration. The fact that 2 of the 5 largest earthquakes ever recorded happened within 7 years of each other, both in subduction zones that had not been considered capable of producing events of that size. Now examine what happened after the cluster. From January 2019 through the present, a span of approximately 7.5 years, the global record contains between 5 and 7 magnitude 8 or larger events. The annual rate is approximately 0.7 to 1 event per year, essentially the long-term average. The cluster ended. The pattern that the viral chart implies has continued uninterrupted since 1997, actually concentrated in a 14-year window, then relaxed back toward the mean. This temporal structure matters. It tells you that whatever caused the cluster, if anything specific caused it, was a process that opened in late 2004, persisted for 14 years, and then closed. It is not a permanent regime shift. It is a cluster. And clusters have a different kind of explanation than permanent regime shifts. The 1997 El Niño peaked in November and December of 1997. It dissipated by mid-1998, 6.5 years before the cluster began. The temporal mismatch between proposed cause and observed effect is severe. The viral chart offers no mechanism to bridge a 6.5-year gap. The peer-reviewed literature offers none because no plausible mechanism exists. Climate signals can modulate seismicity on seasonal to interannual timescales. They can also modulate seismicity on centennial to millennial timescales through glacial isostatic adjustment. But there is no known mechanism by which a single climate event in 1997 can store its influence for 6.5 years and then release it as a coordinated sequence of great earthquakes. Beginning in late 2004, the energy budget argument reinforces the temporal argument. A magnitude 8 earthquake releases approximately 6 times 10 to 6 joules of elastic strain energy. A magnitude 9 releases approximately 2 times 10 to the 18th joules. These are among the largest discrete energy releases in the natural Earth system. The 1997 El Niño redistributed enormous amounts of energy in the atmosphere and upper ocean. The total atmospheric kinetic energy reorganization during the event was on the order of 10 to the 19th joules. In absolute terms, that is larger than a magnitude 9 earthquake, but almost none of that energy reaches the lithosphere as mechanical stress. The vast majority is dissipated as heat. The portion that reaches the crust as a coherent stress signal is many orders of magnitude smaller. The sea level change associated with the warm water slosh from west to east is on the order of 10 to 20 centimeters. The resulting stress change on the seafloor is on the order of a few kilopascals. The tectonic stress that had accumulated on the Sunda megathrust before the 2004 earthquake was on the order of several megapascals. a megapascal is 1,000 kilopascals, the El Niño stress signal is 3 orders of magnitude smaller than the accumulated tectonic stress on a fault ready to fail. It can shift the timing of an event by days or weeks. If the fault is already at the threshold, it cannot cause a fault to fail that was not already there. The energy budget fails. The temporal sequence fails. And the counterfactual test fails. The 2015 to 2016 El Niño was comparable in magnitude to the 1997 event. By some measures, it was slightly stronger. If strong El Niños cause sustained elevations of the global magnitude 8 earthquake rate, the 2015 event should have produced a fresh elevation, beginning sometime around 2022 or 2023. It did not. The post-2018 rate has remained at the long-term average. No surge, no second cluster, no signal. The viral chart's causal claim fails 3 independent tests, any one of which would be sufficient to reject it. All 3 together place it firmly outside the range of what the evidence supports. But the failure of the viral claim does not mean nothing is happening. Something is happening. The planet's surface mass distribution is changing. The changes are measurable. The crust is responding. And in the peer-reviewed literature, a different story has been emerging. For the past 2 decades, that story is not about a single event in 1997. It is about a sustained, accelerating anthropogenic redistribution of mass from the cryosphere to the ocean, from the continents to the sea, from the aquifers to the atmosphere. And it is about how that redistribution is slowly, subtly, and persistently modulating the timing of the largest earthquakes on the planet. The seismological community has been debating the post-2004 cluster for nearly 2 decades. The debate is not about whether the cluster occurred. It occurred. The debate is about whether the cluster represents a real change in the underlying earthquake generation process, or whether it is consistent with the normal statistical variability of a process that produces rare events. This is not a trivial distinction. It goes to the heart of how we assess seismic hazard. If the underlying rate has changed, then past occurrence rates are not a reliable guide to future occurrence rates. If the underlying rate has not changed, then the cluster is a statistical fluctuation, and the long-term average remains the best predictor of future activity. The literature divides into 2 camps. The literature camp argues 2 camps. The first, that the cluster is real and statistically significant, and that some global mechanism must be responsible. The most prominent paper in this camp was published in 2005 by Charles Bouffe and David Perkins of the United States Geological Survey. The title was Evidence for a Global Seismic Moment Release Sequence. Bouffe and Perkins argued that you could detect a coherent global pattern of moment release that exceeded what random variation should produce. Their proposed mechanism was dynamic triggering, the idea that great earthquakes in one part of the world could dynamically trigger great earthquakes in other parts of the world through beacon-tropopage of long period surface waves that travel around the planet and momentarily stress distant faults that are already near failure. The second camp argues that the cluster is consistent with the kind of random variation that any rare event process will exhibit over a 14-year window. The most prominent papers in this camp include a 2010 paper by Charles Ammon, Thornley, and David Simpson, titled Great Earthquakes and Global Seismic Networks, a 2011 paper by Andrew Michael, titled Random Variability, explains apparent global clustering of large earthquakes, and a 2012 paper by Peter Shearer and Philip Stark, titled Global Risk of Big Earthquakes has not recently increased. Ammon and his co-authors examined the same data as Bouffe and Perkins, and concluded that the apparent cluster was within the range of what a Poisson process with the long-term rate would be expected to produce. A Poisson process is the standard statistical model for rare independent events. Decay of radioactive atoms, arrival of customers at a shop, occurrence of large earthquakes. The defining property is that the variance in the count over any given time window equals the mean count. For a long-term rate of one event per year over a 14-year window, the expected count is 14. The standard deviation is the square root of 14, approximately 3.7. Observing 18 events in a 14-year window is within 1 standard deviation. Observing 20 is within 2. Neither is statistically significant evidence of a rate change. Michael ran a Monte Carlo analysis. He generated thousands of synthetic earthquake catalogues from a Poisson process with the long-term rate. He asked how often a 14-year window would appear that looked as clustered as the actual 2004 through 2018 window. The answer was that such clustering appeared frequently enough that you could not reject the hypothesis of random variation. Shearer and Stark applied more sophisticated statistical tests, including tests that account for the possibility that the underlying rate has changed gradually rather than abruptly. They reached the same conclusion. The post-2004 cluster was within the noise envelope of the long-term rate. A 2015 paper by Eric Daub, Daniel Trugman, and Paul Johnson performed Monte Carlo simulation done under several different models of earthquake generation, including models that allow for weak clustering of the kind observed in aftershock sequences. Under all models, the conclusion was the same. The cluster could not be rejected as random variation at conventional statistical confidence levels. It is important to understand what these papers are saying and what they are not saying. They are not saying the cluster did not happen. It happened. The Sumatra event was real. The Tohoku event was real. The cluster of great earthquakes between 2004 and 2018 is a feature of the instrumental record. They are not saying the cluster was an illusion. The human eye is not being tricked. The cluster is visible in the data. What they are saying is that the timing of those specific earthquakes relative to one another is not so unusual that you would have to invoke a new global mechanism to explain it. Each event has its own local cause. The cluster considered as a sequence in time is what you would get if those local causes happen to coincide more closely than usual over a 14-year window. No additional mechanism is required. This is the central scientific tension. One group says the cluster is statistically unremarkable. Another group says the cluster is real and demands explanation. Both groups are publishing in the same journals. Both groups are analysing the same data. Both groups are staffed by qualified seismologists. The tension is not resolved. It may never be fully resolved because rare events produce noisy data and noisy data produce ambiguous statistics. But the debate itself is important. It tells you that the question of whether the planet's great earthquake rate has changed is not settled. The confidence intervals are wide. The signal-to-noise ratio is low. Reasonable scientists disagree. What is not in dispute is the cluster's educational consequence. Before 2004, the dominant framework for understanding subduction zone ruptures was the segmentation model. Subduction zones could be divided into segments. Each segment had its own characteristic maximum magnitude. Segment boundaries acted as barriers that would stop ruptures from propagating from one segment to the next. The Sumatra event broke that model. The rupture propagated along 1,300 kilometers of the Sunda megathrust, crossing multiple segment boundaries that had been assumed to be inviolable barriers. The Triutal the region, the total moment release was far larger than any of the individual segment assessments had predicted. The Tohoku event made the same point with a different emphasis. The Japanese National Hazard Assessment had assigned a modest probability to a magnitude 9 event on the Japan Trench segment that ruptured in 2011. The maximum credible magnitude in the pre-event assessments was around 8.3 to 8.5. The actual event released approximately 30 times more energy. The lesson was the same. Subduction zones can produce larger events than the textbook said they could. Segmentation is real, but segment boundaries are not inviolable. Under the right conditions, ruptures can propagate across them. The maximum credible magnitude for most major subduction zones has been revised upward. The concept of supercycles, yin, recurrence patterns over thousands of years that are not visible in the 100-year instrumental record, has become central to hazard assessment. Paleoseismic work, the study of prehistoric earthquakes through buried marsh soils, ghost forest turbidite chronologies, and other geological archives, has been emphasized as essential for understanding what subduction zones are truly capable of. The Cascadia subduction zone is a case study. Before 2004, Cascadia was considered a low probability source of great earthquakes. After the Sumatra and Tohoku events, the paleoseismic record was re-examined. The work of Brian Atwater on buried marsh soils in Washington and Oregon, and Chris Goldfinger on offshore turbidite chronologies, established that Cascadia has produced magnitude 9 events in the past, the most recent on January 26, 1700, and that the average recurrence interval for full margin ruptures is approximately 500 years. The current USGS probability for a Cascadia magnitude 9 event in the next 50 years is approximately 10 to 15%. The probability for a southern segment magnitude 8 event in the same window is approximately 37%. These probabilities are substantially higher than the pre-2004 assessments would have suggested. Modestly, the Nankai True off the southern coast of Japan underwent a similar reassessment. The Japanese Hazard Agency now estimates a 70 to 80% probability of a Nankai magnitude 8 or larger event in the next 30 years. The exposed population includes the cities of Nagoya, Osaka, Kobe, and the surrounding industrial corridor, totaling 20 to 30 million people in the inundation and damage zones of the worst expected scenarios. The Hikurangi margin off the eastern coast of New Zealand was reassessed. The pre-2004 assessments had treated Hikurangi as a relatively quiet subduction zone. The post-reassessment work has revealed evidence of prior large ruptures, including events of magnitude 8 or larger. The exposed population includes Wellington and the surrounding region, the Aleutian Arc, the Kuril-Kamchatka system, the Chilean margin, the Peruvian segment, the Mexican subduction zone, the Cocos Plate interfaces of Central America. The reassessment has been global. The trend has been consistent. Maximum credible magnitudes upward, confidence in segmentation downward, awareness of supercycle behavior upward. This is the tectonic context in which the climate modulation story must be evaluated. We now know that subduction zones can produce larger events than previously thought. We now know that the recurrence intervals for the largest events are longer than the instrumental record, which means we cannot rely on the past 100 years to tell us what the next 100 years will bring. And we now know from the climate seismicity literature that the timing and clustering of these events is subject to modulation by climate-driven surface mass redistribution. The modulation is small. It operates at the percent level. It shifts timing. It does not create events that would not otherwise occur. But small effects accumulate over decades, and the mass redistribution that is driving the modulation is accelerating the scientific tension. The scientific is not about whether the modulation exists. It exists. The tension is about whether the modulation matters for the largest earthquakes. The largest earthquakes are rare. Their statistics are noisy. Detecting a small timing modulation against a noisy background is difficult. Some seismologists argue that the signal is too small to be detectable. Others argue that the signal is real and that we are only beginning to develop the statistical tools to quantify it. The honest answer is that we do not yet know. The data is incomplete. The time series is short. The natural variability is high. The signal, if it exists, is small, but the direction of the effect is clear. Climate-driven mass redistribution is transferring mass from the cryosphere to the ocean, from the continents to the sea. The crust is responding elastically. The stress changes are real. They are in the direction of modifying the normal stress on faults, and the regions experiencing the largest mass changes are the regions where the largest earthquakes occur. High-latitude subduction zones, continental margins, regions of rapid groundwater depletion. The scientific tension is productive. It is driving the development of better statistical methods, better geodetic models, better integration of satellite data with seismic catalogues. The tension is not a sign that the science is broken. It is a sign that the science is alive. But for the populations living near the world's most dangerous faults, the tension is not abstract. They need to know what to prepare for. They need building codes, evacuation plans, early warning systems, insurance. The hazard maps that inform these decisions are based on the best available science, which includes both the statistical uncertainty and the upward revision of maximum credible magnitudes. The climate modulation signal is not yet incorporated into operational hazard assessments, not because it is being suppressed, because the amplitude is small and the statistical confidence is low. Operational hazard assessment requires a higher standard of evidence than exploratory research. That is how the system is designed. It errs on the side of not changing the maps until the signal is clear. The signal may become clear in the coming decades. The mass redistribution is accelerating. The crustal response is cumulative. The seismic catalogue is growing. At some point, the signal-to-noise ratio may cross the threshold where operational updates are justified. That point has not yet arrived, but it is closer than it was a decade ago. The human consequences of great subduction zone earthquakes are measured in seconds, minutes, hours, days, weeks, and years. The seconds are the rupture. The ground shakes. Buildings collapse. Bridges fall. The shaking lasts for several minutes in the largest events. For a magnitude 9 earthquake, the rupture propagates along the fault at approximately 3 kilometers per second. A 1,300 kilometer rupture takes over 7 minutes to complete. In those minutes, the ground motion can exceed the acceleration due to gravity. Objects become airborne. Structures designed for static loads fail under cyclic loading. The pattern of failure depends on the local geology. Soft sediment amplifies shaking. Bedrock attenuates it. Landslides are triggered. Liquefaction occurs. The surface behaves like a fluid. The minutes after the shaking are the tsunami window. In a subduction zone earthquake, the seafloor is displaced. The displacement is vertical. It pushes the overlying water column upward. The water spreads outward at the speed of a jet aircraft. In deep ocean, the wave height is small, perhaps a meter. The wavelength is hundreds of kilometers. The wave passes beneath ships without being noticed. As it approaches the coast, the seafloor shoals. The wave slows. The wavelength decreases. The height increases. By the time it reaches the shore, it can be 10, 20, 30 meters high. It arrives in surges that can last for hours. In the 2004 Sumatra earthquake, the tsunami reached the coast of Banda Aceh within 15 minutes. The wave height exceeded 30 meters in some locations. The population had no warning. The wave swept over the city. More than 160,000 people died in Aceh province alone. In the 2011 Tohoku earthquake, Japan had one of the most sophisticated early warning systems in the world. Seismic alerts were issued within seconds. The tsunami warning was issued within 3 minutes. The population had approximately 10 to 30 minutes of lead time depending on location. Nearly 20,000 people still died. The wave overtopped seawalls that had been designed for smaller events. It inundated areas that had been considered safe. The Fukushima Daiichi plant lost backup power. The reactors melted down. The evacuation zone remains uninhabitable. The consequences of a great earthquake are not limited to the shaking and the tsunami. There are secondary consequences. Fires. The shaking ruptures gas lines. The tsunami spreads the fires. Firefighting infrastructure is damaged. Water mains are broken. Fires burn uncontrolled. In the 1923 Great Kanto earthquake in Japan, fire killed more people than the shaking. Landslides. The shaking destabilizes slopes. The landslides can dam rivers. The dams can fail. The failure can produce flash floods. The combination of shaking, sliding, and flooding can isolate communities for weeks. Disease. The disruption of water and sanitation systems leads to outbreaks of cholera, typhoid, and other waterborne diseases. The overcrowding of evacuation centers facilitates the spread of respiratory and vector-borne diseases. The health system, already damaged and overwhelmed, cannot respond effectively. The economic consequences are measured in billions to hundreds of billions of dollars. The 2011 Tohoku earthquake cost approximately $250 billion, making it the most expensive natural disaster in history. The 2004 Sumatra earthquake cost approximately $110 billion. The 1995 Kobe earthquake cost approximately $100 billion. These costs are not abstract. They represent destroyed infrastructure, lost productivity, disrupted supply chains, uninsured losses, insurance premium increases, government debt. The financial consequences of a great earthquake propagate through the economy for years. Across the region, the human consequences also include displacement. After the 2011 Tohoku earthquake, more than 340,000 people were displaced. Many never returned to their homes. The evacuation zone around Fukushima remains largely empty more than a decade later. The communities that were destroyed have not been rebuilt. The population has aged. The young people have moved away. The towns are dying. After the 2004 Sumatra earthquake, more than 500,000 people were displaced in Aceh alone. The displacement lasted for years. The reconstruction took more than a decade. The psychological trauma of displacement, of losing one's home, one's community, one's sense of place, is not captured in economic statistics. The populations exposed to great subduction zone earthquakes are large and growing. Coastal cities are expanding. The number of people living within the inundation zone of a major tsunami has increased by hundreds of millions over the past half-century. The concentration of infrastructure in coastal areas has increased even faster. Ports, airports, power plants, lights, refineries, data centers, manufacturing facilities. The critical systems that keep modern economies functioning are disproportionately located in coastal areas, because coastal areas have been historically advantageous for trade, because coastal areas are where the population is, because the risk was not fully understood when the infrastructure was built. The risk is now better understood. But the infrastructure remains. The Cascadia subduction zone exposes approximately 7 million people in the Pacific Northwest to a full margin magnitude 9 event. The metropolitan areas of Seattle, Tacoma, Portland, Vancouver and Victoria are within the shaking zone. The coastal communities of Oregon and Washington are within the tsunami inundation zone. The probability of a Cascadia magnitude 9 event in the next 50 years is 10 to 15%. The probability of a southern segment magnitude 8 event is 37%. These probabilities are high enough to justify substantial investment in preparedness. Some investment has been made. Oregon and Washington have upgraded their building codes. Tsunami evacuation routes have been mapped. Vertical evacuation structures have been built in some communities. Schools and hospitals have been retrofitted. But the gap between what has been done and what needs to be done remains large. Many schools in the Pacific Northwest are still vulnerable to collapse. Many bridges are still vulnerable. Many hospitals are still vulnerable. The cost of full retrofitting across the region is measured in tens of billions of dollars. That cost has not been funded. The Nankai exposes 20 to 30 million people in Japan to a magnitude 8 or larger event. The probability in the next 30 years is 70 to 80%. Japan has invested more in earthquake preparedness than any other country. Building codes are strict. Early warning systems are advanced. Tsunami barriers are extensive. Public education is widespread, but the Nankai event remains a profound concern. The economic cost of a Nankai earthquake is estimated at $1 to $2 trillion. The number of fatalities is estimated in the tens of thousands to low hundreds of thousands. The displacement could reach millions. The impact on the Japanese economy, and by extension on global supply chains, would be severe. The Lima metropolitan area in Peru exposes approximately 10 million people to the Peru-Chile Trench. The trench has produced very large earthquakes in the past. The 1868 Arica earthquake is estimated at magnitude 9. The 1966 Peru earthquake was magnitude 8.1. The recurrence interval for great earthquakes on the Peruvian segment is on the order of 200 to 300 years. The last great event was in 1746. The region is overdue in a statistical sense. The population of Lima has grown by millions since the last major earthquake. The infrastructure is not prepared. Many buildings are unreinforced masonry. The coastal geology amplifies shaking. The tsunami would arrive within minutes. The Bay of Bengal coast exposes hundreds of millions of people to the Sunda megathrust. The 2004 Sumatra event demonstrated what the southern segment can do. The northern segments off the coast of Myanmar and northern Sumatra have not ruptured since at least 1762. The strain has been accumulating for more than 250 years. The population in the affected areas has grown from tens of millions to hundreds of millions. The cities of Chittagong in Bangladesh, Yangon in Myanmar, and Chennai in India are within range. The tsunami would cross the Bay of Bengal in a few hours. The warning infrastructure is limited. The evacuation capacity is limited. The potential death toll in a worst-case scenario is measured in hundreds of thousands to millions. The Aleutian Arc exposes the coast of Alaska and the Hawaiian Islands to great earthquakes and tsunamis. The 1946 Aleutian earthquake produced a tsunami that killed 165 people in Hawaii. The 1957 Aleutian earthquake produced a tsunami that caused damage across the Pacific. The 1965 Aleutian earthquake was magnitude 8.7. The recurrence intervals are irregular but short on geological timescales. The population of Hawaii is approximately 1.4 million. The warning system has improved since 1946. But the wave would arrive in hours, not minutes. Enough time for official warnings. Not enough time for full evacuation of coastal areas. The New Zealand Hikurangi margin exposes the North Island east coast to a magnitude 8 or larger event. The cities of Wellington, Napier and Gisborne are within range. The tsunami would arrive within minutes. The population is approximately 1 million in the exposed areas. New Zealand has invested in preparedness. Building codes are strong. Warning systems are in place. Evacuation routes are mapped. But the scale of the potential event is large relative to the size of the country's economy and emergency response capacity. These are the direct exposures. The populations living within reach of a great subduction zone, earthquake, and tsunami. The total is in the hundreds of millions, possibly approaching 1 billion when you count all of the major subduction zones around the Pacific and Indian Oceans. The indirect exposures are everyone else. Global supply chains pass through the ports, located in these coastal cities. The 2011 Tohoku earthquake disrupted semiconductor production for months. The global automotive industry felt the impact. Production lines idled, prices rose. The disruption propagated through the economy in ways that in ways that were difficult to predict and impossible to fully prevent. A larger event in a different location would produce larger disruptions. The port of Shanghai, the port of Los Angeles, the port of Rotterdam, the port of Busan. These are the nodes through which global trade flows. They are all located in coastal areas. They are all vulnerable to tsunami inundation. Some more than others, but none are invulnerable. The insurance industry models these risks. The models are based on historical catalogues. The catalogues are short. The uncertainty is large. The models are updated as new data becomes available. The post-2004 reassessment of subduction zone capabilities forced a major update. The climate modulation signal has not yet been incorporated, not because it is being suppressed, because the signal is small and the statistical confidence is low. The insurance industry is conservative. It waits for clear evidence before changing its models. But the direction of the evidence is clear. The planet's surface mass is being redistributed. The redistribution is accelerating. The crust is responding. The timing of great earthquakes is being modulated. The modulation is small. It operates at the percent level. But small effects accumulate over decades, and the accumulation is just beginning. The human consequences of this accumulation will not be visible in any single earthquake. They will be visible in the statistics, a slight increase in the rate of great earthquakes, a slight clustering of events in time, a slight reduction in the average interval between events. The differences will be small enough that they may not be detectable for decades, but they will be real, and they will matter, because the difference between a great earthquake happening today and happening next year is not just a matter of statistics. It is a matter of preparedness. A community that has 30 years to prepare is different from a community that has 15. A community that has 5 years is different from a community that has 1. The timing modulation shifts the probability distribution. It changes the odds. It does not guarantee a particular outcome, but it tilts the table. The communities that are already prepared are better off regardless of the timing. The communities that are not prepared are worse off. The timing modulation makes the consequences of unpreparedness more severe, because it increases the probability that the event will occur before the preparation is complete. The human consequences of the climate modulation signal are therefore mediated by the pace of preparation. The signal is slow, the preparation is slow. The race is not dramatic. It is a slow accumulation of risk on one side and a slow accumulation of resilience on the other. Which side wins will determine how many people die in the next great earthquake. A single great earthquake is a cascading effect in itself. The rupture triggers shaking. Shaking triggers landslides. Landslides trigger dam failures. Dam failures trigger floods. The tsunami triggers more flooding. Flooding triggers disease. Disease triggers displacement. Displacement triggers political instability. Political instability triggers economic contraction. The cascade propagates through systems that were designed to operate independently but are in fact tightly coupled. The 2011 Tohoku earthquake demonstrated this cascade. The shaking triggered the tsunami. The tsunami overwhelmed the seawalls. The seawater flooded the backup generators at Fukushima Daiichi. The generators failed. The reactors lost cooling. The fuel melted. The containment was breached. Radioactive material was released. The evacuation zone was established. The zone remains largely empty. The cascade took weeks to unfold, but the connections between the links were not visible in advance. The engineers had designed the seawalls to withstand a certain size tsunami. They had located the backup generators above the height of the seawall. They had not anticipated that the tsunami would overtop the seawall and flood the generators. The failure was a failure of imagination. The imagination was constrained by the historical record. The historical record did not contain an event as large as Tohoku. The engineers assumed the maximum credible event was smaller than it turned out to be. The post-Tohoku reassessment of subduction zones was an attempt to expand the imagination, to incorporate paleoseismic evidence, to consider supercycles, to revise the maximum credible magnitudes upward. The reassessment was successful in the sense that the hazard maps were updated. But the reassessment cannot tell you when the next event will occur. It can only tell you that the probability is higher than previously thought. The climate modulation signal adds another layer to the cascade. The mass redistribution from cryosphere loss, sea level rise, and groundwater depletion is not uniform. It is concentrated in specific regions. The regions experiencing the fastest ice loss are high-latitude coastal margins, Southeast Alaska, the Antarctic Peninsula, Greenland, Iceland. These are also regions of significant tectonic activity. The interaction between ice loss and fault loading is just beginning to be studied. The principle is straightforward. Ice loss reduces the load on the crust. The crust rebounds. The rebound produces stress changes. The stress changes affect the failure probability of nearby faults. The effect is small per year. But the ice loss is accelerating. The cumulative stress change over decades is not negligible, and the faults in these regions have long recurrence intervals. The last great earthquake in southeast Alaska was in 1958, the Lituya Bay earthquake. Magnitude 7.8. It produced a mega tsunami that stripped vegetation from slopes up to 520 meters above sea level. The recurrence interval for great earthquakes in this region is on the order of several hundred to 1,000 years. The ice loss stress signal is small relative to the tectonic stress, but it is not zero and it is one-directional. It is pushing the fault toward failure. Not today, not next year, but over the coming decades and centuries, the cascading effects of a great earthquake in a high-latitude region with rapid ice loss would be different from a great earthquake in a mid-latitude region. The ice itself could be destabilized. A large earthquake in Greenland could trigger ice quakes. Ice quakes are seismic events within the ice sheet itself. They are caused by ice fracturing. They are small relative to tectonic earthquakes. But a large tectonic earthquake could trigger a cascade of ice quakes across the ice sheet. The ice quakes could in turn trigger additional fracturing. The fracturing could accelerate ice flow. The accelerated ice flow could increase the rate of mass loss. The increased mass loss would further reduce the load on the crust. The reduced load would further promote fault failure. The cascade would be slow. It would operate over years to decades. But it would be real. This is speculative. There is no direct observational evidence of such a cascade. The timescales are too long. The events are too rare. But the physics is plausible, and the possibility is being modelled. The cascading effects of sea level rise on subduction zone seismicity operate on different timescales. Sea level rise increases the load on the seafloor. The increased load increases the normal stress on faults. Increased normal stress inhibits failure, so sea level rise should slightly suppress seismicity. But the effect is small. The cumulative sea level rise over the past century is approximately 25 centimeters. The associated stress change is a few kilopascals, 3 orders of magnitude smaller than the tectonic stress. The direction of the effect is suppression. But the magnitude is tiny, and sea level rise is not uniform. It is amplified in some regions by ocean dynamics and reduced in others. The regional pattern matters. A region experiencing faster than average sea level rise will experience faster than average stress increase. The stress increase will slightly delay the next great earthquake. A region experiencing slower than average sea level rise will experience a smaller delay. The relative timing between different subduction zones will shift. The clustering of great earthquakes in time could be affected, not dramatically, but measurably over centuries. The cascading effects of groundwater depletion on seismicity are better documented. The Central Valley of California has been losing groundwater for decades. The loss is measured by grace. The surface expression is subsidence. The land is sinking. But the deeper crust is responding elastically. The Sierra Nevada is rising. The uplift is measured by GPS. The uplift produces stress changes in the eastern California shear zone. The stress changes have been correlated with changes in seismicity. The correlation is small, a few percent modulation, but it is detectable, and it is caused directly by human activity. The water being pumped from the Central Valley Aquifer is being used for agriculture. The agriculture produces food. The food feeds people. The people live in cities. The cities are built on the Pacific coast. The Pacific coast is a subduction zone. The connections are indirect, but they exist. The cascading effects of a great earthquake on groundwater systems are also real. The shaking can increase permeability. Increased permeability can cause water levels to rise or fall. The changes can persist for years. The changes can affect agricultural productivity. The changes can affect drinking water supplies. In regions already stressed by groundwater depletion, an earthquake can push the system over a threshold, not dramatically, but measurably. The cascade propagates from the lithosphere to the hydrosphere to the biosphere to the human system. The cascading effects on infrastructure are the most immediately visible. A great earthquake damages ports. Damaged ports cannot handle cargo. Cargo that cannot be handled does not reach markets. Markets that do not receive cargo experience price increases. price increases affect consumers. The cascade propagates through the global economy. The 2011 Tohoku earthquake disrupted the supply of automotive microcontrollers for months. The disruption affected every major automaker in the world. The cascade was not predicted. The supply chains had been optimized for efficiency, not resilience. The optimization assumed that the system would not experience a shock as large as Tohoku. The assumption was wrong. The next great earthquake will occur somewhere. It will damage something. The damage will propagate. The propagation will be different from Tohoku because the global economy has changed. Supply chains have been reorganized. Some have been diversified. Others have become more concentrated. The resilience of the system is not obvious. It will be tested. The climate modulation signal does not create new cascades. It shifts the timing of the events that trigger the cascades. The shift is small, but the consequences of the shift are not necessarily small. A great earthquake that occurs 10 years earlier than it would have otherwise occurs in a different economic and political context. The context matters. The preparedness of the affected region matters. The state of global supply chains matters. The geopolitical situation matters. The pandemic status matters. The climate conditions matter. The cascade is shaped by the context. The context changes over time. The timing modulation changes the context in which the cascade unfolds. This is the deepest level of the climate modulation story. It is not about the direct effect of mass redistribution on fault failure. That effect is small. It is about the indirect effect of shifting the timing of rare events into different contexts. A great earthquake that would have occurred in 2050 occurring instead in 2040 or 2060. The difference is not large in geological terms, but in human terms, it is the difference between a world that has prepared and a world that has not, between a world with stable supply chains and a world with disrupted ones, between a world at peace and a world at war. The cascading effects are not determined by the earthquake alone. They are determined by the earthquake plus the context. The context is shaped by human decisions. The decisions are made in the present. They affect the future. The climate modulation signal makes the future less predictable, not because the signal is large, because the signal changes the probability distribution in ways that are difficult to model. The uncertainty is irreducible. The best we can do is to understand the range of possible outcomes and to prepare for as many of them as possible. The future of great earthquake occurrence on this planet will be shaped by three overlapping factors: tectonic strain accumulation, climate-driven mass redistribution, and the natural statistical variability of rare event processes. The first factor is well understood. The second is becoming better understood. The third is irreducible. Tectonic strain accumulation is the rate at which plates converge. The Pacific plate moves northwest relative to North America at approximately 5 centimeters per year. The Nazca plate moves east relative to South America at approximately 7 centimeters per year. The Indian plate moves north relative to Eurasia at approximately 5 centimeters per year. These rates are stable over centuries to millennia. They are not affected by climate change. The total seismic moment that must be released by the global subduction system over any given century is therefore approximately constant. The climate modulation signal does not change the total. It changes the timing. Climate-driven mass redistribution is the rate at which ice is lost from the cryosphere, the rate at which sea level rises, and the rate at which groundwater is depleted. These rates are accelerating. The acceleration is driven by anthropogenic greenhouse gas emissions. The emissions are continuing. The concentration of carbon dioxide in the atmosphere is now approximately 420 parts per million. The pre-industrial concentration was 280 parts per million. The difference is 140 parts per million. That difference is driving the warming. The warming is driving the ice loss. The ice loss is driving the mass redistribution. The mass redistribution is driving the crustal response. The crustal response is modulating the timing of great earthquakes. The natural statistical variability of rare event processes is the fact that earthquake occurrence is not periodic. It is not perfectly regular. It is clustered. The clustering is not fully understood. It is partly intrinsic to the fault system. The failure of one fault can trigger the failure of another. The triggering can be dynamic or static. Dynamic triggering is the passage of seismic waves. Static triggering is the permanent change in stress. Both have been documented. Both contribute to clustering. The statistical variability is large. The confidence intervals are wide. The uncertainty is irreducible. Projecting the future of great earthquake occurrence requires combining these three factors. The tectonic strain accumulation sets the baseline. The climate modulation signal shifts the baseline slightly. The natural variability adds noise. The projections are probabilistic. They are not deterministic. They cannot tell you when the next great earthquake will occur. They can only tell you the probability that a great earthquake will occur within a given time window. The current state of the art in probabilistic seismic hazard assessment incorporates tectonic strain accumulation and natural variability. It does not incorporate climate modulation. The reason is not cross suppression. The reason is that the climate modulation signal is small and the confidence in its amplitude is low. Operational hazard assessment requires a higher standard of evidence. The evidence is not yet high enough, but the evidence is growing. The GRACE and GRACE follow-on missions have produced a continuous record of mass redistribution since 2002. The record now spans more than 2 decades. The trend is clear. The ice loss is accelerating. The acceleration is strongest in Greenland and West Antarctica. The sea level rise is accelerating. The acceleration is driven by the ice loss. The groundwater depletion is continuing. The depletion is strongest in the Central Valley of California, the high plains of the United States, the North China Plain, the Indo-Gangetic Basin, and the Middle East. The crustal response to this mass redistribution is being measured by GPS networks. The networks have been densified over the same period. The records are now long enough to detect trends. The Sierra Nevada is rising. Southeast Alaska is rising. Iceland is rising. The Antarctic Peninsula is rising. Greenland is rising at its margins. The rates are small, but they are persistent and they are accelerating. The stress changes associated with this crustal response can be modelled. The models require assumptions about mantle viscosity, lithospheric thickness, and fault geometry. The assumptions introduce uncertainty, but the range of possible stress changes can be bounded. For Greenland, the cumulative stress change from ice loss over the past 2 decades is on the order of 10 to 30 kilopascals. That is small relative to the megapascal scale of tectonic stress, but it is not zero, and it is one-directional. The stress is being relieved, the crust is rebounding, the normal stress on faults is being reduced. Reduced normal stress promotes failure. For the subduction zones adjacent to rapidly rebounding regions, the effect is a slight increase in the probability of failure. The increase is small, perhaps a fraction of a % per decade, but the baseline probability is also small. The recurrence intervals for great earthquakes on most subduction zones are measured in centuries to millennia. The annual probability is on the order of 0.1% to a few percent. An additional fraction of a percent per decade is a small absolute increase, but it is not negligible in the context of long-term hazard assessment. For the subduction zones that are not adjacent to rapidly rebounding regions, the effect is different. Sea level rise adds load to the seafloor. The added load increases normal stress. Increased normal stress inhibits failure. The effect is again small, a fraction of a percent per decade. But in the opposite direction, the overall effect of climate-driven mass redistribution on global seismicity is therefore a regional patchwork. Some regions experience a slight increase in probability, others experience a slight decrease. The net effect on the global rate is small, probably too small to be detected in the catalogue over the next few decades, but detectable over the course of a century. The post-2004 cluster of great earthquakes was not caused by climate-driven mass redistribution. The timing does not match. The cluster began in 2004. The ice loss signal was already present in 2004, but it was smaller than it is today. The cluster ended around 2018. The ice loss signal has continued to grow. If the climate signal were the dominant driver, the rate would have continued to increase. It did not. The cluster was most likely a statistical fluctuation, a streak of bad luck within the normal variability of a rare event process. The streak was real. The events were real. The damage was real. The deaths were real. But the underlying cause was not a change in the global rate. It was the alignment of local conditions that happened to produce more events in a short period than average. It is a statistical inevitability. It is a statistical inevitability. The question is when. The climate modulation signal will shift the timing slightly. The shift is too small to predict. But the direction is predictable. The regions experiencing rapid ice loss will have a slightly higher probability of failure. The regions experiencing sea level rise without ice loss will have a slightly lower probability. The net effect on the timing of the next cluster is unknown. What is known is that the planet is changing. The mass redistribution is real. The crustal response is real. The stress changes are real. The effects on fault behavior are real, though small. And the acceleration of mass redistribution is real. The Greenland ice sheet is losing mass faster now than it was a decade ago. West Antarctica is losing mass faster. The mountain glaciers are losing mass faster. The rate of sea level rise is increasing. The rate of groundwater depletion is increasing in many regions. The projections for the remainder of this century are sobering. Under current emissions trajectories, the Greenland ice sheet will continue to lose mass. The loss will accelerate. The West Antarctic ice sheet will continue to lose mass. The loss may become irreversible. The mountain glaciers will continue to retreat. Many will disappear entirely. The sea level rise by the end of the century is projected to be between 1/2 and 1 metre, possibly more, if ice sheet dynamics are faster than the models predict. The cumulative mass redistribution over the next 75 years will be enormous. The Greenland ice sheet contains enough water to raise global sea level by 7 metres. Most of that ice will not melt this century, but a significant fraction will. The West Antarctic ice sheet contains enough water to raise sea level by 3 to 4 metres. The most vulnerable sector, the Amundsen Sea embayment, is already in irreversible retreat. The ice loss from this sector alone will contribute tens of centimetres to sea level rise by the end of the century. The stress changes in the crust beneath and around these regions will be correspondingly large. not large enough to cause a great earthquake by themselves, but large enough to measurably modulate the timing of great earthquakes that would have occurred anyway. Rister paused. The future of great earthquake occurrence is therefore not independent of the future of climate. The two systems are coupled. The coupling is weak. It operates through the elastic response of the crust to surface mass redistribution. But it is real, and it is becoming better understood. The scientific community will continue to refine the models. The statistical methods will improve. The geodetic networks will densify. The satellite records will lengthen. The signal-to-noise ratio will increase. At some point, the climate modulation signal may become large enough to incorporate into operational hazard assessments. That point is not yet here, but it is approaching. For the populations living near the world's most dangerous faults, the approach of that point is not abstract. It means that the hazard maps they rely on to make decisions about building codes, evacuation planning, and insurance are incomplete. They do not yet include the climate signal. The signal is small, but the consequences of ignoring it are not necessarily small. A small shift in probability can have a large effect on expected losses when the baseline probability is small and the exposed value is large. The honest projection is this. Over the next several decades, the rate of great earthquakes will fluctuate around the long-term average. The fluctuations will be dominated by natural variability. The climate modulation signal will be visible in the statistics only after many decades of accumulation. The signal will be most visible in the regions experiencing the fastest mass redistribution: Southeast Alaska, Greenland, Iceland, West Antarctica, the Antarctic Peninsula. These regions will see a slight increase in the probability of great earthquakes. The increase will be small, but it will be real. The rest of the world will see little to no climate-driven change in great earthquake probability over the next several decades. The tectonic strain accumulation will continue to dominate. The hazard will remain. The uncertainty will remain. The need for preparedness will remain. The future of this planet is not determined by any single factor. It is the product of many factors interacting over many scales: tectonic, climatic, statistical, human. The interactions are complex. The outcomes are uncertain. The only thing that is certain is that the planet will continue to change. The change will continue to be measured. The measurements will continue to inform the models. The models will continue to improve, and the improvements will continue to reveal new connections between systems that were once thought to be separate. The climate modulation of great earthquake timing is one of those connections. It is not the most important connection. It is not the most urgent, but it is real, and it is a reminder that the Earth is a single system. The ice, the ocean, the crust, the atmosphere, the biosphere. They are not separate, they interact. The interactions are slow, but they are cumulative, and over time, cumulative interactions reshape the planet. The viral chart that circulated online was wrong. The 1997 El Niño did not cause a 93% increase in the global rate of magnitude 8 earthquakes. The energy budget fails. The temporal sequence fails. The counterfactual test fails. The chart was a misdiagnosis, a real pattern in the data attached to the wrong cause. But the chart was not wrong about everything. It was wrong about the mechanism. It was not wrong about the observation that something has changed. The global rate of magnitude 8 earthquakes in the post-1997 window is higher than in the pre-1997 window. The increase is not a fabrication. The data is real. The pattern is real. The interpretation is where the error lies. The real mechanism is not a single event in 1997. It is a sustained, accelerating, anthropogenic redistribution of mass across the surface of the planet. The Greenland ice sheet is losing mass. The West Antarctic ice sheet is losing mass. The mountain glaciers are losing mass. The global ocean is rising. The aquifers are being drained. The crust is responding. The response is elastic. The response is measurable. The response is modulating the timing of great earthquakes. The modulation is small. It operates at the percent level. It does not create earthquakes that would not otherwise occur. It shifts the timing of earthquakes that were going to occur anyway. The shift is not dramatic. It is not visible in any single event. It is visible in the statistics. And the statistics require decades of accumulation to become clear. The scientific community has documented the climate modulation of seismicity for small to moderate earthquakes. The Himalayan monsoon, the Japanese snowpack, the California groundwater cycle, the Mississippi basin loading. The effects are real. They are published. They are not suppressed. They are simply not widely known outside the specialist literature. For great earthquakes, the signal is more difficult to extract. The events are rare. The statistics are noisy. The natural variability is high. The climate signal, if it exists, is small. The debate is ongoing. Reasonable scientists disagree. The disagreement is productive. It is driving the development of better methods and better models. The human consequences of great subduction zone earthquakes are not debated. They are known. The shaking kills. The tsunami kills. The fires kill. The landslides kill. The disease kills. The displacement destroys communities. The economic disruption propagates through global supply chains. The insurance industry absorbs losses. The governments borrow money. The taxpayers pay the debt. The cycle repeats. The populations exposed to great subduction zone earthquakes are large and growing. Hundreds of millions live within reach of a major tsunami. The infrastructure is vulnerable. The preparedness is incomplete. The gap between what has been done and what needs to be done is large. The gap is measured in billions of dollars and decades of work. The climate modulation signal does not change the fundamental nature of the hazard. It does not make the hazard go away. It does not make the hazard worse in any dramatic sense. It shifts the timing. It changes the probability distribution. It tilts the table. A region that was already at risk remains at risk. A region that was not at risk does not become at risk. The modulation is subtle, but subtlety matters when the consequences are measured in lives and dollars. The future of great earthquake occurrence on this planet will be shaped by tectonic strain accumulation, climate-driven mass redistribution, and natural statistical variability. The first factor is well understood. The second is becoming better understood. The third is irreducible. The projections are probabilistic. They are not deterministic. They cannot tell you when the next great earthquake will occur. They can only tell you the probability that a great earthquake will occur within a given time window. The probability is not zero. It will never be zero. The Earth is an active planet. The plates are moving. The faults are loading. The earthquakes are inevitable. The only uncertainty is when the climate modulation signal adds a small additional layer of uncertainty. It shifts the distribution. It does not eliminate the distribution. The range of possible outcomes remains wide. The confidence intervals remain wide. The irreducible uncertainty remains. What the climate modulation signal does is to remind us that the Earth is a single system. The systems we study separately are not separate. The cryosphere is connected to the lithosphere through mass redistribution. The hydrosphere is connected to the lithosphere through loading. The atmosphere is connected to the lithosphere through pressure. The biosphere is connected to the lithosphere through the activities of one species, a species that is currently redistributing mass on a planetary scale. The redistribution is not intentional. It is the unintended consequence of burning fossil fuels, pumping groundwater, and changing the land surface. The consequences of the redistribution are not intentional either. They are the mechanical response of a planet to a changing load. The viral chart was an attempt to make sense of that response. It was a crude attempt. It was flawed. It was wrong in its causal claim. But it was born from a real intuition that something has changed and that the change is not being adequately communicated. That intuition was correct. The communication gap is real. The peer-reviewed literature is not reaching the audiences that need it. The gap is filled by viral charts, social media posts, and conspiracy hashtags. Not because people are stupid, because the existing channels of science communication are failing. This documentary is an attempt to bridge that gap. Not by simplifying, by doing the opposite, by walking through the data, the instrumentation, the mechanisms, the debates, the uncertainties, the human consequences, the cascading effects, the future projections. The conclusion is not dramatic. It is not alarming. It is observational. The planet is changing. The changes are measurable. The changes are affecting the timing of great earthquakes. The effects are small. They are real. They will continue. They will accelerate as the mass redistribution accelerates. They will be felt by the populations living near the world's most dangerous faults. They will be felt indirectly by everyone else through the global systems that depend on coastal infrastructure. The chart was wrong, but the impulse behind the chart was not wrong. Something has changed. The change is not the 1997 El Niño. The change is the cumulative result of 2 centuries of anthropogenic forcing. The forcing is ongoing. The consequences are unfolding. They will continue to unfold for the rest of this century and beyond. The earthquakes are coming. The earthquakes were always coming. What has changed is the planet they are landing on. The planet we are making is the one that will determine who survives and who does not when the next cluster opens its window and begins to release the slip that has been quietly accumulating for centuries beneath the cities where most of us live. That is not a warning. It is an observation. It is what the data shows. It is what the instruments measure. It is what the models project. It is what the scientific literature documents. It is not a cause for panic. It is a cause for attention, for preparation, for continued measurement, for continued modelling, for continued communication. The Earth is speaking. Its language is not words. Its language is mass redistribution, crustal rebound, stress change, earthquake timing. The language is slow. It operates on decadal to centennial timescales. But it is audible to those who have built the instruments to hear it. The satellites, the GPS networks, the seismic catalogues, the paleoseismic archives. The message is not simple. It is not reducible to a single chart. It is not a single event in 1997. It is the cumulative story of a planet being reshaped by the species that lives on it. The story is still being written. The next chapters will be written by the data that comes in over the coming decades. The data will be collected by the same instruments, analysed by the same methods, debated by the same community, communicated through the same broken channels. The job of this documentary has been to walk through the story as it stands today, with the data we have, with the models we have, with the uncertainties we have. The story is not finished. It will not be finished in our lifetimes. The timescales are too long. The processes are too slow. The interactions are too complex. But the direction is clear. The planet is changing. The change is accelerating. The change is affecting the timing of great earthquakes. The effects are small, they are real, they will matter. That is the final reframe. The viral chart asked the right question and gave the wrong answer. The right answer is slower, larger, less dramatic, and more disturbing. It is the answer that emerges from the data. The data does not panic, the data observes. The data measures. The data accumulates. The data speaks in probabilities, not certainties. The data is the only thing we have. Listen to it.